Welcome to this explainer. Today we're going to completely demystify the core concepts of physics. And we're going to do it by exploring a scenario that, well, we honestly all know entirely too well. That's right, we're talking about your daily commute.
So what if I told you that the totally mundane drive you take every single morning is actually a literal masterclass in physics? It's true. Today we're going to unpack exactly how the science of motion works, and the best part, absolutely no intense math or complicated formulas are required here. We're just going to look at the world right outside your car window. Okay, let's dive right into this. I want you to imagine you're sitting in the driver's seat right now. You're turning the key, you shift the car into reverse, and you're preparing to leave your house. Believe it or not, this simple, everyday action is the absolute perfect starting point for our journey into classical mechanics. To study motion, we obviously first need to know where we're starting from. In this case, your driveway serves as your starting reference point. In the study of physics, specifically a field called kinematics, this is formally known as your position. It's usually represented by the letter X, and it's simply where an object is located relative to a specific reference point. Now, as you pull your car out of the driveway and onto the street, you've moved, right? That physical movement from point A to point B is what we call your displacement. Displacement is quite literally just your change in position. A minute ago, you were sipping coffee in the driveway. Now you're out on the street. You have been displaced. Let's visualize this drive as you head down your neighborhood street. If we actually mapped your car's changing positions second by second, a really predictable pattern pops up. At 1 second, you've moved 10 meters. At 2 seconds, 20 meters. At 3 seconds, 30 meters. You're just cruising along at a very steady pace. And mapping it out like this brilliantly illustrates how we can visualize motion. If we plot those data points onto a simple position time graph, we get a perfectly straight upward sloping line. That straight incline proves without a doubt that you are maintaining a constant speed. With every passing second, you're covering the exact same amount of ground. Now, speed is great and all, but in kinematics, we actually use a slightly more specific term. That steady speed, combined with the specific direction your car is heading down the street, let's say you're driving north towards the city, is defined as your velocity. So velocity tells us how fast your position is changing, sure, but it absolutely always includes the direction you're going. But hey, your commute isn't just a slow, steady crawl through the neighborhood forever, right? Eventually you hit the highway on-ramp, and the physics completely shift when you press down on that gas pedal to merge into fast-moving traffic. Your steady, straight line is about to change dramatically. So, the crucial point we need to make here is the distinct contrast between velocity and acceleration. Velocity simply means going fast, like when you're cruising at a steady 60 miles per hour. But acceleration, that is the act of getting faster over time. It's how your velocity actually changes. When you mash that gas pedal to merge, you aren't just moving, you are accelerating. Notice how your speed actively stair-steps upwards with each passing second of your merge. Second 1, you're going 30. Second 2, you're at 45. Second 3, you hit 60. This upward stepping of velocity over a period of time is the very definition of acceleration. Let's switch gears to a slightly new example to see how all this builds. Imagine you've finished a snack and you toss an apple core out your car window into a ditch. Or, if you'd rather, imagine throwing a ball to a dog at the park. This action totally transitions us from a one-dimensional, straight-line drive into two-dimensional motion. Much like throwing that ball at the park, throwing any object through the air creates what is known in kinematics as projectile motion. It's considered a two-dimensional motion, and here's why. The object is moving forward horizontally, yes, but it's also simultaneously being pulled downward vertically by gravity. What's really fascinating about this is that the thrown ball doesn't just drop straight down to the ground the exact moment it leaves your hand. Because it has that forward velocity we talked about, but is also being yanked downward by gravity, it's forced along this curving, arc-like trajectory. In the physics world, we call this a parabolic path. So let's do a quick recap of the environments we've covered so far. Whether it's a car on a straight road representing 1D straight-line motion, a thrown ball representing 2D projectile motion, or even spinning objects and orbiting planets representing circular motion, these pretty much cover the core types of motion that are mapped out by kinematics. But wait a second, here is the big reveal from our source material today. Think about everything we have just mapped out together. Position, velocity, acceleration, parabolas. Do you notice anything missing? Everything we've discussed entirely ignores your car's actual engine or the physical muscles in your throwing arm.
And this brings us to a really massive distinction. Kinematics strictly describes the what of motion, basically the math of the movement itself. But dynamics, which is another branch of classical mechanics, explains the why. Dynamics looks at the real-world forces, like a heavy foot on a gas pedal or the explosive power of an engine that actually cause the movement to happen. Separating the movement from the force is an incredibly powerful tool in science. It lets us predict exactly where something will end up without having to calculate complex engine mechanics or individual muscle twitches every single time. To put it simply, kinematics is just the tracking mechanism. It strictly answers questions like, where are things located? How fast are they changing position? Are they speeding up or slowing down? It completely ignores the invisible forces pushing and pulling them. It is purely the geometry of motion.
Okay, let's lock in this knowledge with 3 quick practice questions. We'll start with your steady highway commute. Here's the scenario. If you are driving a constant 60 miles per hour on a perfectly straight highway, what is your acceleration? Take a quick second to think about our definitions.
The answer is 0. Why? Because remember, acceleration only occurs when your velocity is actively changing. If you are just stuck there cruising at a constant 60 miles per hour, your speed isn't stepping up or stepping down. Therefore, 0 acceleration.
Fantastic. Okay, for our second question, think back to our example of the tossed apple core or playing a fun game of fetch. You throw a ball to your dog at the park. What specific type of motion is this called in the world of kinematics?
That's right, it's projectile motion. That distinct, curving, parabolic journey through the air, driven forward by your throw, but pulled constantly downward by gravity, is the absolute textbook definition of 2D projectile motion. All right, final practice question for you. Does the field of kinematics care about the horsepower inside your car's engine? Say you're trying to calculate the sheer force required to physically move a 2-ton vehicle. Are you using kinematics for that? Exactly. The answer is no. Engine power is a force, meaning it fundamentally belongs to the study of dynamics. Kinematics just maps the resulting journey, the speed, the acceleration, the overall distance, while dynamics explains the raw forces that actually made that journey possible in the first place. As we wrap up this explainer, I want to leave you with a final, slightly deeper thought to ponder. If kinematics can reliably map the physical journey of literally everything in the universe, from a car backing out of a suburban driveway to massive planets spinning in the void of space, what invisible dynamics and forces are driving your own personal trajectory forward today? Something to think about. Thanks so much for joining me, and keep exploring the fascinating physics hidden in your everyday life.